Oh, so it's the nth derivative, whatever the power is, it's the nth derivative of the first Laplace, of it to the first power.
Yeah, this is saying, you know, the Laplace of t to the n, f of t, okay, is just equal to -1 raised to the n, and then you take the nth derivative with respect to s. Let me write the s as a triangle, okay, of f of s. Already? So the reason that this is helpful is because let's say I was trying to find, I'll give you an example here. Let's say I was trying to find the Laplace of let's just say here, like say t to the 5th cosine 5t, for example. Let's say I want the Laplace of this. Okay? Now, of course, if you're going to try to apply the standard definition, you're going to have to integrate this, and you're probably going to run into integration by parts. It's actually not even going to be possible. Yeah. It's going to be very difficult to do that integral.
Yeah.
So what this theorem allows you to do, it says, okay, great. This is your f of t. Go and find the Laplace of that. Okay? So we're going to find f of s for cosine 5t. Okay? For cosine 5t. And the way you do this is here you don't have to integrate. You can use the definitions of, you know, the table of Laplace, where the cosine is turns out to be, let's see where it is. The table is somewhere here. So the cosine of, say, bt, in this case b is 5, is s over, okay, s squared plus b squared, and since b is 5, so this is s squared plus 25. Okay?
Yeah.
And what this definition enables you to do, actually, let's change this 5 so we don't have to work like a long problem here. Let's just say that this was the second derivative, the t squared instead of t to the 5. Okay? So what this theorem enables you to do, it says, okay, take the Laplace of that, right? And then in this case, of course, your n equals 2. And then it says that the Laplace of t squared cosine 5t will just be -1 to the n, so -1 to the 2, times the derivative. What derivative? The nth derivative. So the second derivative over ds of s over s squared plus 25. That's what it's saying. So this becomes -1 squared is just 1 times. You take the first derivative, so quotient rule, so with respect to s. So 1 times the denominator minus the top times the derivative of the bottom over s squared plus 25 squared. That's the first derivative, and then we do another derivative of this derivative. Okay? So this was the first derivative. We can simplify this So this is minus 2s squared, so this is minus s squared, because s squared minus 2s squared is minus s squared, plus 25 over s squared plus 25. I mean, it's still a little bit tedious in terms of derivatives, but it's a lot less tedious than having to actually go and do the integral or the definition of Laplace. So here you need another quotient rule. So it'll be minus 2s times the denominator as is, right? Minus the derivative of the denominator, so 2s squared plus 25 to the 1 times the inside times the top as is, minus s squared plus 25, all over s squared plus 25 squared, so it becomes to the 4. I can cancel out one of these, right? So I would get minus 2s times s squared plus 25 minus 4s squared into minus s squared plus 25 all over s squared plus 25 cubed. Okay, we can simplify more than this, but you get the idea. The point here is not derivatives. So this is the Laplace transform of what example did I give? T squared cosine 5t. Which would have been really, really tough to do using the integral. Probably impossible because you're going to get an exponential on top of it. So this is what this theorem enables you to do. Solve questions like this. Okay? Questions on what I did and how to illustrate the use of this theorem?